Hey guys, so today's lecture is going to be over groundwater, and we're just going to talk a bit about what groundwater is, how it moves, and how it is stored, and how it is able to alter the landscape. So at the end, we get to talk about three super cool things that groundwater does, and it's always one of my favorite things to talk about in class. So first, let's start by talking about what is groundwater. So here's the hydrologic cycle again. We looked at this in the streams lecture whenever you watched that. So remember in the rivers lecture, we talked about how stream runoff is an important component of the hydrologic cycle. But there are also a number of other processes happening in the water cycle. So we have evaporation and transpiration, where we're turning liquid water into water vapor, and then that's hanging out in the atmosphere as clouds until it's precipitated down. And once it's precipitated onto the landscape, it can do one of two things. So over here in the diagram here, I'll highlight precipitation for you. And once it precipitates onto the landscape, it can either run off as stream flow and enter into the ocean, or it can infiltrate into the ground and become part of the groundwater portion of the hydrologic cycle or the water cycle. So today we're focusing on this process of infiltration or percolation into the ground of this precipitation, and then how that water is moving within the ground um, as a part of the hydrologic cycle. So infiltration is how we get water into the groundwater system. And so the fancy definition of infiltration, if we're thinking of it scientifically and not in military terms, is the process of water sinking into the ground. And so infiltration is going to increase when you have a gentle land slope. It's going to increase when the land is lightly vegetated. It will increase when you have moderate to gentle rainfall, and it increases when you have relatively dry soil. So our infiltration rate will increase when we have a gentle slope on our landscape, when we have light vegetation, when we have moderate to gentle rainfall, and when we have relatively dry soil. So if we were in class, we would have partnered with somebody to think about or talk about why infiltration increases under those four circumstances. So go ahead and take a second, think, write it down. Why does infiltration increase when we have a gentle land slope, when land is lightly vegetated, when we have moderate to gentle rainfall, and when we have relatively dry soil? So groundwater is one of those guys that's very aptly named. It is just the water that's held within the ground. So it's just the water that's below the Earth's surface. It's being held in cracks and spaces within the soil and the rocks that are underneath us. So soil, sand, and rocks all are holding groundwater. And there are two physical properties. Those are called porosity and permeability, that are largely controlling the amount of groundwater that's held within a certain rock layer and how fast or well that groundwater is moving around. So that first physical property is something called porosity. So in a rock, in a sediment or a sedimentary rock or any type of rock, you have some open spaces within that we call pores. And so in this diagram over here, you can see that we have solid pebbles. Those are our sediments. And then in between our particles, we have a bit of open space. Those particles aren't completely compacted all the way together so that you don't have any open space at all. And so that open pore space is what you call a pore. And so pores can include that space between particles, and it can also include any cracks or holes that are within your rock material. And so porosity is a measurement, and so it's just a percentage of the total open volume of space, pore space. So you can have low porosity, which means that you have a low percentage or a small percentage of total volume of open space. And you can have a higher porosity where you have a high percentage or a big percentage of total volume of open pore space within your sediment, within your rock. So take a minute to think about what are some features or processes that can explain the porosity within a sediment or a rock. So think back to when we talked about how rocks form and think about some of those processes or features that might explain why you would have open space within a rock. So I turned my video off for this slide so that you can see the whole diagram over there on the right-hand side. So hopefully you've had some time to think about how porosity might change with some of those processes of rock formation. And so let's go over the top 3 ways that porosity is affected. So first, porosity is affected by sorting. So remember when we learned about sedimentary rocks, we learned that some sedimentary rocks are made up of grains that are all the same size, and that means that it's well sorted. And some sedimentary rocks are made up of grains that are all different sizes, and that means that they are poorly sorted. So over here on our diagram, we can see that the poorly sorted guy over here has a low porosity, and that's because all of the small particles can get into the space in between the large particles and can overall effectively fill in a lot of pore space that way. As we move over to the right in this diagram, towards well sorted, you can see that more and more of this tan background is present, and that's because in our well sorted material, when things are all the same size, they can only get so close together, and then there's nothing to fill in that pore space. There's no smaller particles to fill in that pore space in between them. So this means that if you have better sorting, the more well sorted something is, it's going to have a higher porosity. So porosity increases with sorting. Something to consider is if we have 2 materials, let's say we have a coarse sand and we have something made up of pebbles, but both of those materials are made up of sediments that are all the same size. So we have 1 millimeter coarse grained sand grains, and we have 2 centimeter pebbles, and they're all those size, and we're looking at 2 different rocks. If those different rocks are both made up of spheres of the same size uniformly within that rock, and they are packed the same, then they will have the same porosity. So sorting can't always determine porosity, and so we also have to consider packing. So if you have more tightly packed grains, you're going to have lower porosity. So hopefully that makes sense in your head. As you pack things tighter and tighter together, then you're going to have less pore space because there's just going to be less space between those particles because you packed them together more closely, right? So I sort of think of like those vacuum bags that were all the rage for a while, where you sort of like loosely pack something in there and then you vacuum all the pore space, all the air out of it, and it becomes tightly packed. So loosely packed sediments are going to have more pore space, higher porosity. Tightly packed sediments are going to have lower porosity. And then finally, grain rounding is important. So as you get more round grains, you're going to have higher porosity. So if you have pointy angular grains, here it's listed as non-spherical, then they're able to, all those points and angles on those grains are able to pack very closely together and decrease the amount of pore space. But spheres can only get so close together before they can no longer be packed or put together any farther. And so spherical grains, the rounder our grains are, means that we are going to have more pore space. This picture here is just to show that not only is porosity impacted by grain sorting, packing, and rounding, but it is also impacted by fracturing or dissolution within your rocks. So if we're going to increase porosity when we have fracturing or any type of dissolution cavities within our rocks, and we're going to decrease our porosity through compaction and cementation. So as rocks get more compacted and more cemented, they are going to decrease in porosity. So the first physical property that's important for groundwater amount and flow is porosity, and the second physical property is permeability. And so permeability is just the ease of water to flow, and it's related to how interconnected the pores are. So you can think of this as the capacity or the ability of a rock to transmit fluids. So you can have something with totally isolated pores that are not interconnected at all, which is probably how we all feel right now sitting at home, not being very interconnected and isolated, right? Those materials are called impermeable. They're not able to transmit water very well at all. And we can also think of permeability in terms of low and high permeability, just like we thought of porosity as in terms of low or high porosity. So low permeability materials are not allowing water to flow very readily, and then high permeability materials allow water to flow very readily. So down here, B is an example of a really high permeability material where we can see the water is flowing really easily through these interconnected pores, right? Water is able to move in between those pores very easily. So there's also some words that we use to characterize groundwater. So groundwater occurs in two different zones. The first zone is called the unsaturated zone. It's also sometimes called the aeration or vadose zone. So in this zone, we have the pores are mostly filled with air or water vapor. Sometimes there's a small amount of water in the unsaturated zone. So up here we have our unsaturated zone, also sometimes called the zone of aeration. And you can see that in this zone, we have mostly white pores. That's indicating that there's mostly air or water vapor within those pores. You can see water is weird and it has really strong surface tension, right? So we have a little bit of water held in between our particles in here through surface tension or molecular attraction. And then the second zone is called the saturation zone, the saturated zone, or it's sometimes also called the ferritic zone. And this is when all of your pore space is filled with water. So we can see down here in our zone of saturation that all of our pore space is filled with water with that blue down there on the bottom. And the layer or the distinction between the two, the top of the saturated zone is called the water table. So here I'll draw or highlight the water table for you. So the water table is the upper surface of the saturated zone and is sort of the delineation between the saturated and the unsaturated zone. You can also have some perched water tables occurring in the unsaturated zone if you have some impermeable layer that water sort of builds up on top of. And I'll show you an example of a perched water table here in a little bit. So now let's talk about how groundwater moves. So when we're thinking about groundwater movement, we typically refer to something called an aquifer, which is just a permeable zone of rock or sediment that is transmitting water economically. So aquifers are places where you have high porosity, so you have lots of pore space, and high permeability, so that pore space is well connected. And when you have high porosity and high permeability, water is able to easily move through that medium. And when water can easily move through a medium and it can move quite quickly, then we refer to that as transmitting water economically. So on this diagram, we have something called an unconfined aquifer here at the top, which we will get to here in a second. And then down here, we have a confined aquifer at the bottom. So here you can see we have high porosity and permeability. We have lots of pore space, and that pore space is well connected. And an aquitard is an impermeable bed where water is not moving very quickly and water is moving too slowly to be economical. So here we have our aquitard, highlighted it in green for you. In this zone, we have low porosity and low permeability. So water's not moving through these layers very well at all. Some examples of good aquatards are clays and shales. So this is why they generally line, what's it called? The landfill, like if you've ever heard of them lining landfills with clays, that is to sort of help to mitigate transmitting pollution from the landfill down into the groundwater using an aquatard or a layer of low porosity and low permeability. So thinking of aquifers, there are two types of aquifers. There are unconfined aquifers and confined aquifers. So unconfined aquifers are connected to the surface by open pore spaces, and so they can be recharged or they can get water from the surface really easily because they are unconfined and they are open for exchange with water with the atmosphere. And so the amount of water within an unconfined aquifer is indicated by the height of the water table. And then in confined aquifers, these are permeable rock units. So you have a good aquifer where you have high permeability, high porosity, but that rock unit is enclosed within some type of impermeable strata. So you have some impermeable layers sort of protecting your aquifer from exchange with the atmosphere. And so these are typically found much deeper and they aren't readily able to recharge widely with the atmosphere, but instead they recharge at high elevation where those rocks are exposed. So here's an example of those types of aquifers. So here's our unconfined aquifer up at the top, right? So this blue layer here is our unconfined aquifer. You can see that you're readily able to exchange with the atmosphere. We have our water table here at the top. And then we have a confining layer here. Three confining layers. So clay, really low permeability, not very economically able to transmit water. And then within and sandwiched in between those confining layers are two confined aquifers. So we have two confined aquifers. See how they're sandwiched in between those confining layers. So you can drill down into a confined aquifer, drill a well down into a confined aquifer, which is probably a good idea if you can afford to drill down into a confined aquifer to sort of get unpolluted or less likely to be polluted waters. And then, as I mentioned, there's something called a perched aquifer or a perched water table. And a perched aquifer is just an unconfined aquifer that is sitting above the regional water table or the regional unconfined aquifer. So in this diagram over here, you can see here is our impermeable layer. On top of our impermeable layer is our unconfined aquifer. Remember that the unconfined aquifer is marked at the top by the water table, which is shown by that blue dashed line. But up in our unsaturated zone, so here is our unsaturated zone, we have another impermeable layer, sort of locally, of clay, and then there's another one over here. And water builds up on top of that and creates something called a perched water table. So a perched water table is just an unconfined aquifer that's sitting above the regional water table. Humans extract water from the groundwater system using wells by drilling wells. So a lot of you are at home and you might have well water at home and get all of your water for your home or your town from well water. And so something that happens when you drill wells is called the cone of depression. And so let's, over here on the left-hand side, let's look at this undeveloped landscape where we have a water table. And then we have a little bit of, let's say, development into agricultural land, and we have maybe a major agricultural corporation come in and they have lots of money, so they they drill a really deep well, and then maybe we have, Farmer John over here who drills a smaller well for his smaller agricultural system. And so over time, what happens is we start to get this cone of depression where when you are extracting water from the system, just like when you suck water through a straw, you get this draw down around the well extraction zone, and that creates this little cone shape that we call the cone of depression. And as you keep extracting, what's going to happen is little Farmer John's well over here is going to dry up. So eventually the cone of depression is going to be so severe that this major well is okay, but it is affecting a lot of the shorter wells around. And of course, here's a picture of a dog in the cone of depression, right? So not that type of cone of depression, but the cone of depression that is associated with well extraction. Okay, guys, so next are the 3 super awesome things groundwater does. So I don't want you guys to think groundwater is boring. Some of the stuff at the beginning, like porosity and permeability, it's like, why do I care really about groundwater? Okay, we're extracting it with wells, but it also does some cool stuff. So we get to talk about that now. And I'm super bummed because this part is one of my favorite things to lecture about. So please be excited about the 3 super awesome things. So first, you guys know it's my favorite place, Yellowstone. Over here, this is a picture of my favorite place in Yellowstone, Grand Prismatic Springs. But the first super awesome thing that groundwater does is that it creates thermal springs and geysers. So geysers and hot springs are basically the most spectacular manifestation of groundwater. So geysers happen when you have a hot spring that intermittently erupts jets of hot water and steam. So we have scalding hot water commonly erupting into the air, and these are occurring in places where you have recent volcanic activity. So geysers require you have to have a hot body of rocks lying relatively close to the surface. So that hot body of rocks is related to volcanic activity. You have to have some system of fractures that's extending downward from the surface, and you have to have a relatively large supply of groundwater available. So you have to have some hot rocks, you have to have fractures extending down from the surface, and you have to have lots of groundwater. So we're going to have groundwater, we're going to heat it up, and it's going to rise up through those fractures to create an eruption of hot water in the form of a geyser. So here, this diagram is just showing how a geyser erupts. So here in this first part, up in this corner right here, you can see we have groundwater that's circulating through those hot rocks. So that red color on the bottom is trying to show you that these rocks are hot. And we have groundwater circulating within there. And then that groundwater starts to flash to steam in this next diagram. And when that groundwater turns into steam, think of like a tea kettle, right? You have expanding steam that's starting to force water upward until it is going to be discharged at the system. And then once you force some water out, you're going to reduce that pressure. So we are erupting water out to try and reduce the pressure. And then once that pressure is decreased enough, then your eruption is going to cease and all the steam has been released and the geyser tubes are empty. And then what happens is these chambers start to fill back up with groundwater. That groundwater gets heated up like in a kettle, right? We have steam. We're going to push that steam and water out of the system. That water is going to flash to steam, and then you get the steam discharge of this erupting hot water geyser, and the process just repeats itself. The second super awesome thing groundwater does is that it erodes away soluble rocks. So it doesn't actually erode things away like you might think of breaking them into smaller particles. What it does is that it's going to dissolve large quantities of these rocks. So think of those rocks that are reacting in hydrochloric acid, limestone, dolostone, gypsum, rock salt. Those things are going to be dissolved and carried away. Those little ions are going to be carried away in solution. So this happens in the saturation zone where you have groundwater moving through rocks through a process called carbonate weathering. So I just put up this chemistry if any of you are interested in chemistry. But basically what happens is that water and carbon dioxide combine and create something called carbonic acid. And that carbonic acid can react with calcite in rocks to form calcium and bicarbonate ions in solution. And then those ions get carried away from the system and effectively dissolve away large amounts of rocks. When you're dissolving away lots of rock in the saturated zone, you get something called karst topography, which is super cool. So the subsurface dissolution is forming sinkholes and caves. So lots of caves and sinkholes are formed through this dissolution process, and we refer to all of those things that are formed through dissolution as karst topography. So because it's just this catch-all term to talk about things that are formed from subsurface dissolution, karst topography can be super highly diverse, but they're all related because they have really soluble rocks. So for example, in China, there's these mountains caused by dissolution, but also generally think of just caves and sinkholes and those examples that we have in the US. So this is just a map of the US karst topography that we have. Sorry, North Dakota, we just have this little teeny tiny blip down here in the southeastern corner of the state. And that is related to, as we can see, some carbonate rock weathering. So I'm from Indiana, as you guys know, and I'm sure I talked about too much. But, you know, as a kid, we grew up going to caves and things. So caves are super cool. If you've never been to a cave, you should definitely go sometime. So you'll notice that most of our karst topography in the U.S. is these green colors, which is related to our carbonate rocks. Think of our limestones, our dolostones, marbles. But there are also some weird examples of evaporite rocks in Texas, Oklahoma, New Mexico sort of general area. And then there's also some volcanic dissolution or dissolution of volcanic rocks happening in sort of the volcanic western portion of the US. So caves and sinkholes are both examples of karst topography, but they form a little differently. So caves are forming through that weak acid dissolution process that's building, that is dissolving away the rock and leaving these open cavities that are then later either exposed at the surface or found through a system of channels and tunnels. But sinkholes are caverns that are also formed through dissolution, but they start to grow and grow until their roofs collapse. So the difference between a cave and a sinkhole is a cave's roof is not going to collapse, but a sinkhole, its roof is eventually going to collapse. And so the formation of caves versus sinkholes really depends on how well held together or stuck together the material on top or at the Earth's surface is. So remember, caves and sinkholes are being formed in the saturated zone. In the unsaturated zone, that's what we call the overburden. If the unsaturated zone is really well stuck together, then you're going to form a cave. But if you have an overburden that's not very stuck together, that's really crumbly and it's going to fall apart and it can't hold the weight on top of this hole that's formed underneath it, then the top will eventually fall in and create a sinkhole. So on the next slide, sort of my favorite story to tell about sinkholes is the Corvette Museum in Bowling Green, Kentucky, actually had a sinkhole open up in it, thankfully overnight, but it damaged a bunch of sort of irreplaceable Corvettes. And so I always like to show this footage because it is super crazy. Now at the museum, they have restored some corvettes. They have kept some of them the way that they are. So now at that museum, they have like a little information about karst topography in a car museum, which is super cool. So please watch that YouTube video because it's super interesting. So if you like cars and are interested in what corvettes actually went into the sinkhole, this is the list of the corvettes that were damaged during that sinkhole incident. It included like the 1 millionth built Corvettes and some signed cars and a pace car and a design car that was never actually built. So some pretty irreplaceable things were damaged in that sinkhole. So as I mentioned, in South China, there is also something called tower karst, which is actually this weird type of karst where the land surface used to be, here I'm drawing with yellow for you, all the way up here, and the land dissolved away, everything except these sort of weird looking mountains that are left behind. And so this is a sort of weird example of karst topography. Up here, if you look at it from an aerial view, you can see it looks kind of pockmarked, and it's just sort of really strange the way that they dissolved, right? They dissolved into these sort of rounded mountains. And it's so weird that they used this in Star Wars Revenge of the Sith to film the Wookiee planet. So the next slide is a YouTube video of that footage if you want to sort of try and peek at the tower karst in the background. Super awesome thing 3 that groundwater does is that it actually deposits things as well. So we have geysers and we have cave and sinkhole karst topography formation. So we have that erosion dissolution process. And then also in caves, you start to get deposition caused by groundwater as well. So in the saturated zone, we are going to be eroding away material, but in the unsaturated zone, we are going to be able to deposit material using groundwater. So we have dissolved a bunch of stuff into our groundwater in the saturated zone, and that mineral matter that has been dissolved can be deposited in lots of ways in caves, and we collectively call those speleothems. So think of stalagmites and stalactites and all of those sort of cave deposits. Those are collectively known as speleothems. So remember, deposition of groundwater is happening in the unsaturated zone. So think of your stalactites and stalagmites. And remember, I know the difference between the two from elementary school because stalactites hold tight. They also have a C because they're on the ceiling. They're holding tight to the ceiling. And then stalagmites have a G because they are found on the ground. So that's how you tell the difference between a stalactite and a stalagmite. Some less obvious forms of deposition by groundwater include lots of sandstone cements or sedimentary rock cements. So remember when we talked about sedimentary rocks and we said, okay, these grains get compacted and cemented together, and we never really talked about how they got cemented together. Well, one way that that happens is through this deposition of groundwater in the unsaturated zone that's creating mineral structure in between grains or in the pore space. This diagram is just showing some examples of speleothems and other karst topography. So we can see up here we have an example of a sinkhole. So you can see how this was a cavity that then the top collapsed on. You can see some stalactites holding tight. So there's some stalactites. Here's some stalagmites. You can also get some other sort of really cool things, drip curtains, collapse into your cave system, and so on and so forth. This slide is just some cool pictures of cave deposits or groundwater deposition. So we have some cool cave deposits over here on the left-hand side. And then over on the right-hand side and the right top, we have some petrified wood. So this is wood that's been fossilized by groundwater running through it and replacing the original wood material with minerals. In the middle here, we have a geode. right, which is that sort of a hollow rock that minerals have crystallized inside of. And then on the far right here is travertine deposition of in a hydrothermal environment.